Lovely. Yeah, we had at least 30 sign up, so
We've got 6 people queuing at the moment, Andrew, to sign in.
hello. People are still signing in, aren't they? So this this is this is good. This is good. But is our speaker all happy? Good, good, good. Well, yeah, yeah. Bringing rocks all the way from St Andrews is certainly so. Yes, I suppose. Yes, it's a shame. It's a shame I can't be there because I really quite like this stuff. But you'll have to give Adrian Finch my regards anyway. So.
Right, good evening everyone. I think it's about time we started off tonight. Welcome to every one of you coming for what promises to be a very, very interesting lecture tonight, which Nick's going to give us in a few moments. But before all that, we've got to go through a few little formalities. The first one is, can you make sure all your phones are switched off? Yes, I'm getting yes signals from everyone there. and there is a fine if you get an alarm on your phone whilst we're in progress. So be ready for it. The other one is, can you all please be aware of where the exits are in the case of a quick evacuation. But there are signs up everywhere, so that'll lead you out to the front of the building. The President will give you a welcome in a few moments, but before that, there's some sad news in that our Secretary, Erwin Thompson, passed away last week. We've only just found out, actually. We did hear he wasn't so well, and we are very sad to hear that. He looked as though he's going to be very, very good for the Institute. He was a good member and he was a fine man. So I wonder if we can give just a minute's silence for Erwin.
Brilliant. Thank you very much, Steve. And thank you very much, Nick, for coming along as well. I hear there's a fantastic suite of rocks available for perusal at during the lecture. Just to say as well, St Andrews has got an absolutely sort of fantastic geology department, lots of great people there, lots of really good economic geology work going on as well. So we're really looking forward to having this lecture this evening. Just to go over the formalities, our last lecture after our AGM in December was given by Professor David Manning of Newcastle. Good attendance, a number of questions, vote of thanks by David Mobbs, and the closing remarks by myself. So if we can have that as a record of the meeting. Our next lecture is actually on Monday, and this will be given by Les Turnbull, and it will be a joint lecture with the Newcomen Society. And this will be a follow-up lecture regarding Les's recent publication on the Stockton to Darlington Railway and the earlier history of railways before that. So I'm sure that this is already proving very popular, so do please check that one out. And just to say, our February lecture will be given by Rod Young of Bar Hill on the Rotten Water Transfer Tunnel. Rod is regional manager of Bar Hill and is also outgoing president of the British Tunnelling Society. So all good things there. Don't forget, if you want to keep up to date with all of our events, we're on all the usual channels, so do please go and sign up to those. We've got plenty on for those who are attending for the first time, plenty of lectures and conferences, of which you're currently at one. We're putting together our annual dinner and symposium. Further details will hopefully be forthcoming within the next month or so. Regular socials, and of course the occasional field trip. And if Nick would like to take us off to see any of these rocks, then that'd be superb if we could tag along. Of course, the best way to support our institute is through membership. We've got lots of things on offer, so don't forget to go and look at mininginstitute.org.uk/membership for more information. And with that, I shall pass back to Steve and, of course, Nick to give the introduction. So I hope you all have a very pleasant evening.
Thank you very much indeed, Andrew. In the meantime, Andrew, do you have any apologies for absence that have been sent direct to you?
I believe Paul Kelly and that's the only one, and Keith Hutchinson.
Yes. Sorry? Yes, yes. Right, I have Stuart Porthouse, Malcolm Tilley, who isn't very well. He's out of hospital, but he can walk now, so we'll be seeing him again soon. Don't worry. St. Paul Kelly. Wonderful. Right. We've been through the minutes of the last meeting. So tonight I've got to introduce you to Nick, who's actually going to give us a really interesting talk tonight on battery metals and the race to net zero. I'm surprised the rest of the world isn't in here to hear about this, so, but we did try to tell them, Nick. Anyway, Nick's a geologist and senior lecturer at the University of St Andrews. His research is applications of geochemistry to problems of crustal growth and evolution, specifically focusing on early Earth geodynamics and lithium-tin mineral deposits, with cousin projects in Namibia, Zimbabwe, South Africa and Greenland. I'll leave it to Nick to tell you everything else, because I could go on for a long time with the history of where he started off and what he's doing now. So it gives me great pleasure now to put you in touch with Nick Gardiner, who's going to give you this wonderful lecture this evening. Thank you very much, everyone.
All right. Thank you. All right, thanks very much. Great. Okay. Well, thank you. Thanks for coming. Thanks for inviting me. It's good to come south of the border and get a bit of sunshine before I have to go back north later on today. And thank you for that introduction. So yeah, my background. Is that okay? There's not a feedback. All good. Okay. I shall tag along with the technology. Right. So. This picture is taken in Namibia, in the Wies region, which is in sort of western Namibia, and this is one of the areas where we've been working recently. And this is kind of, old mining explorers talk about elephant country, and there are elephants in Namibia, but what they mean is that, this is the kind of place that if you want to find lithium pegmatites, this is where you go and look. And so we've managed to link in with a local mining company who have a couple of active pegmatite exploration projects in this area, and this is kind of sort of ground zero for global lithium resources, and not just geologically. It's very interesting from a sort of geoeconomic and geopolitical point of view, really. So we are fortunate to be able to go to places like this with PhD students and with postdocs and work with the explorers to try and help them better understand what they're actually looking for. And so it kind of, pure science can be great, but applied science is feels like it has a real purpose. And also, as we'll talk about today, things like lithium is obviously the metal of the moment. How's this? Oh, there we go. Right, so a little bit of background of myself. So, thank you. Yeah, I'm at University of St Andrews. I'm a geologist, I'm a petrologist, a little bit of a geochemist. I previously worked in sort of metamorphic petrology, then I worked in metals trading for a while, and I came back to academia. And I've largely done work around sort of tin and lithium deposits mainly in developing countries, actually, which is sort of very interesting places to work. We have the pegmatites and lasers group up at St Andrews. I didn't name it, that was the PhD students that name it, mainly because we look at pegmatites and we have a laser ablation laboratory, so it seems to work quite well. So we're the pals. And I work with colleagues at Oxford, the BGS, and a few other universities in the UK and beyond. And really what we try and do is understand, the petrological foundation, as I say, for how we develop metalliferous melts. So how do we form the granitic type of melts that ultimately become pegmatites? And we do that from the bottom up. So we use geochemical tools like geochronology, we try and date them. We use different other isotopic tracers, though I won't bore you with the details. There's a sort of picture of the lab in the top right corner. Actually, there's a sort of mass spectrometer. We do field work. We do classic petrography. We're trying to pioneer sort of the idea of looking at metal contents of different accessory minerals to monitor metal growth through these systems. And we do phase equilibrium modeling. And towards the end of the talk, I'll dive in a little bit deeper about some of these aspects. Some of you may be geologists, some of you may not be. But largely, I want to talk today around sort of, metal supply and metal demand with a focus on lithium, then a focus on sort of pegmatites more specifically, and then some of the work we've been doing around. And I'll try and keep it at a sort of fun and accessible level and not go sort of too deep into, there's no isotope plots, you'd be glad to know. I don't think there is. Okay, so, you know, the context for a lot of our work is obviously the energy transition, regardless of, you know, prevailing political climates. It feels like there's still a bit of a critical mass behind decarbonisation. And, you know, this is a huge societal challenge, and it fundamentally means a shift in the sort of how the resource bases of our society. Instead of mining for oil, we're going to start mining for metals. And this puts huge pressure on metal supply. And this, I'm sure this isn't a surprise to people in the room. There's been a lot of talk about this over the last 2 or 3 years. But, you know, if you believe we can meet the Paris Agreement targets, then this sort of net zero pathway puts enormous pressure on the supply of a whole range of different metals. And arguably, the biggest non-political challenge to achieving those goals is the supply of the raw materials to actually enable that. So, given the latency of mining projects, these are urgent problems. What it means is that, you know, as geologists and as engineers and as explorers and as miners, we will need a lot more exploration and a lot more mining of a whole range of different metals, not just lithium, to try and meet these targets. This is very urgent, but it has, you know, challenges for geologists, academic and practicing geologists, engineers, technicians, and beyond, but it also has big economic challenges, geopolitical challenges, and environmental and societal implications as well. And this is one reason why I really enjoy working in this space, because it's not just a geological problem. So, you know, that's kind of the context within which we try and work. Sorry, this is a bit fuzzy. I didn't realize it was so fuzzy. It must be the Mac to PC transition that we were struggling with about an hour ago. But yeah, when we talk about battery metals, we're mainly talking about lithium-ion batteries. So lithium-ion batteries were developed by Sony in the 1980s to power portable electronics. They obviously have evolved since then, and now we talk about them in terms of being core components of electric vehicles. But the technologies have changed. So here's some examples of what metals are in lithium-ion batteries. There's the lithium cobalt oxide battery on the left. There we are. The nickel cobalt aluminium battery, and then various types of what we call nickel manganese cobalt batteries. But one of the common aspects of all of them is obviously lithium. You know, the clue's in the name. And there are various predictions for the types of demand that we will have for these different batteries up to 2050. This is one particular prediction. It's a, you know, very inexact science. And you can see we're looking at manganese. I include copper as well, because that's obviously very important for electrification anyway, nickel, etc. But lithium is by far, you know, almost all these predictions are going to be by far the most, if you like, extreme demand in terms of percentage uptick from today of all the metals. And this has got different scenarios, whether you're looking at the stated policy scenario, which I understand is, you know, when countries stood up at COP26 and said this is what we would do. Then you've got sort of advanced scenarios where you obviously have even more demand of lithium and other metals. But you can see the kind of percentages over the next 20 or 25 years that some people think we were going to need to increase in terms of our metals. So, you know, those are estimates. I put this in as well because this is from the International Energy Authority. They've got very interested in critical metals and critical minerals, obviously, because of the basis for the new energy infrastructure we want to build. And this is also looking at demand versus potential supply. And so in the orange and the yellow, we have different demand scenarios up to 2035, so 10 years away. And again, these are estimates, you know, net zero target kind of predictions. But in the blue, we have what we understand the supply could be. Announced projects, potentially funded projects. Or what So we go back to some of these key metals. You know, many of the other metals, there's a feeling that there could well be enough supply. We don't know. Those predicted projects may fall apart and then we're in a different situation. But according to the IEA, you know, the two most mining constrained metals are copper and lithium. And that's really interesting for, again, for the geologists. So I was going to have a little look at copper. I love this thing on the right. This is from the British Museum. It's a stone tablet from the old Babylonian period of 1750 BC. And it's a letter. It's the complaint that the grade of copper that was delivered was the wrong grade. So, some of the problems that we deal with today are not new. And obviously, copper we've mined for millennia. And most significantly, since the mid-19th century, when we started discovering and using electricity, copper is a really well-established market. So it's a large market. It's a mature market in terms of its supply. It's diversified. There are copper mines all over the globe. So, if there's a coup in Chile and they shut the borders, we can go and get copper from somewhere else. It would be a bit of a hiccup, but it's not a disaster for copper supply. And geologically, we've been studying copper for quite a while. So, again, I put reasonably well understood. People talk about porphyry deposits or sedimentary hosted copper. I'm sure more research could be done, but we have a reasonable constraint, and so the exploration for copper has been fairly successful, and the processing and recycling are reasonably well understood. The big problem with copper, on the bottom left graph, you can see dates from 1990 to a couple of years ago. In the blue are the major copper discoveries per year. And so up until about 2010, we were discovering between 6 and 12 major copper mines per year. Since 2010, we've barely made any copper discoveries. So the big challenge in copper is that, if you like, the big tier 1 deposits have been found. They're the easy ones to be found. We're already mining those, and the next stage of exploration for copper is a lot more challenging. It's perhaps deeper kind of exploration. So we have to use different technologies perhaps to try and find those copper deposits. So I will sort of move on to lithium. I just wanted to make a couple of other points comparing copper and lithium. That they are quite different metals. They're both in batteries or both used for batteries. This is something I show my students in the top right. This is widely available. This shows the tonnages of metals that were dug out the ground in 2019. 96% by tonnage of all metals that were mined was iron ore. So, that kind of dominates mining or metalliferous mining. Then you're looking at copper, about 20 million tons. This is not an insubstantial amount of metal. So it is a major metal, it's industrial metal. And as I talked about, it's quite a mature market. But what we're interested in lithium is up on the top right. So you have lithium, as this work, we've got lithium. There we go. Lithium is there. It's about 100th the tonnage of copper. Tin is there, tantalum is there, cobalt is there. So these specialty metals that we talk about are significantly smaller markets. So, that means that one mine coming on stream or one mine going on strike actually causes a major wobble in the supply of that metal. So the supply of lithium is much more fragile than the supply of copper, for example. And that manifests itself in the price of these metals. So on the bottom left, you can see the commodity prices of lithium here from 2021 to April 2024. And during 2023, the price of lithium swung by about 80%. Copper, on the right is relatively stable. It's still fluctuating. But, one of the challenges if you're running projects around things like lithium and cobalt is the fact that the prices can be incredibly volatile. And it makes, building a long-term mine and building those exploration strategies, and we know that mining is a long-term endeavor. It's not a today, tomorrow, that's it. So the sort of volatility which comes from the fact, in part that these are really small-scale metals does make these really challenging things. But, we need these metals. So that is in part the challenge for explorers and for producers. So I'll talk now onto lithium, I suppose. I got onto lithium about 3 years ago. As I said, I was sort of in the world of tin. Tin was fashionable up until about 1986, and then everyone decided tin was not of interest. I started working in Myanmar in about 2012, 2013, which was a big tin producer. And we got interested in things like tin granites because, my background is how the continental crust forms and evolves, and that's making granites, and granites host tin, and granites also host lithium. So it seemed to be a natural thing to move on to sort of after working on tin. So we got interested in lithium a couple of years ago, and just a bit more about sort of the types of lithium demand we have over the next 10 years or so. So again, take these with a pinch of salt. These are, different prediction made by different analysts. The top right is from SC Insights, the bottom is from Benchmark Mineral Intelligence. But largely, we produce about 1 million tons of lithium carbonate a year globally. By 2028, so 3-4 years' time, that supply will probably need to double. By 2035, that supply may need to quadruple. And that's primarily driven by battery demand. You know, lithium is used in other places, but you know, the principal driver of that demand increase is batteries. So, you know, to put that into context, over the last 5 years, we doubled from 0.5 to 1 million tons at a price that was significantly higher than today. It took 70 years to reach the first 1 million ton of supply. So that ramping up, you know, when we talk about the percentage, is a real structural challenge for lithium markets, because suddenly we just need to, you know, explode the supply of lithium. On the top right, it tries to show, you know, here we are 1 million tons and we want to go up to 4 million or so. So this is what they think are financed projects, potentially unfinanced projects, and then, you know, recycling that could fill the gap. So, you know, in part we don't know where that's coming from, and that's a real problem. But, you know, on the plus side, that's a real opportunity for explorers and for miners and for people producing lithium to actually find those new discoveries. So even though the tier 1 discoveries in copper have been discovered, maybe that still exists for lithium. So I think there's a real, you know, it's a different kind of market, but I think there's a real opportunity. So in terms of the types of deposits, you know, historically there's been 2 main types, and there's a few other types that are coming on stream. The top shows a map of the different, you know, largely the different types. And up until recently, much of the lithium supply came from what we call continental brines or salars, mainly from the so-called lithium triangle in South America, so the Argentina-Chile border, where we have the blue, and up in the high Atacama Desert. And these are lithium-rich brines coming from somewhere in the deep crust. Perhaps they've been intercalating, they've been reacting with maybe lithium-rich volcanic rocks at depth. They're pumped onto the surface, they're evaporated in big pans, and then you harvest lithium salts from that. And, you know, that's been the dominant source of lithium, but what's been sort of creeping up slowly is the second main source, which is hard rock, the pegmatites. So you can see in red are the hard rock pegmatites at the moment. The biggest lithium mine, certainly the biggest pegmatite mine, is the Greenbushes pegmatite in Western Australia. And these are found in orogenic zones, so classic sort of mountain building zones, and also in Archean greenstone belts. And they are sort of granitic type intrusions, quite small scale granitic intrusions. And, you know, from a geographic diversity, we obviously know about a lot more pegmatites. So in many cases, these were originally exploited for things like tin and for cesium. And we're actually going back to some of these old mines and getting the lithium out that wasn't required back in the day. So those are still dominate lithium supply at the moment, and there's a couple of other interesting potentials. So one is the clay-hosted lithium. You may have heard about the Jadar project in Serbia that Rio Tinto has been trying to get up and running for about 2 or 3 years, and that's been stifled in part by public opposition. There's also the McDermott caldera in Nevada, which you can see the green there, and there's the Thacker Pass project there. These are potentially huge sources of lithium. It's basically lithium-rich clays found in maybe volcano-sedimentary basin. You can get clays such as hectorite that are up to about 19,000 ppm lithium. So really rich. The sort of uncertainty there, as far as I understand it, is it's really difficult to define resources. And I think there's still uncertainties around the processing technology about how we actually can industrialize those things. But, you know, the potential for somewhere like Thacker Pass and Rhyolite Ridge to come on stream would make the US, for example, self-sufficient in lithium, which is a bit of a game changer if you think about, you know, weaponization of metals and where metals come from at the moment. And the other interesting source of lithium, which, you know, is of interest in the UK, is this idea of geothermal brines. So there's a project in the Pennines, project in southwest England, which are, again, you know, lithium-rich groundwaters brines that maybe have reacted with a granite at depth, a lithium-rich granite at depth. And lithium is a very mobile element, so it'll easily come out of a rock into a brine. And there's technologies like direct lithium extraction, which instead of sort of passive pan with the cellars, you draw it out in the pan. Evaporation pan wouldn't work so well in the Pennines, but you can have these technologies which actively extract lithium from the brines. So those are other potential sources. What are we doing for time? Okay, so let's go back to lithium-ion battery. I'll come on to the geology very shortly. So where is lithium used? It's really the electrolyte and the cathode. And, you know, I talked about the fact that there are various different types of batteries. And as we've evolved in terms of the batteries we want to use, we are actually evolving in terms of the feedstock. So traditionally, we've used lithium carbonate, which is easily recoverable from the brines, from the cellars, as the main feedstock for lithium-ion batteries. But what's happened over the last 5 or 6 years is there's been a slow shift towards lithium hydroxide as the feedstock. That's harder to get from brines. You have to have a conversion step, certainly the continental brines. But it's preferred because it's the feedstock for higher performance batteries. So if you want your Teslas to be fast, you want a battery that's originated with lithium hydroxide. So these so-called NMC type batteries. And what's that done? What that has actually done is, because lithium hydroxide is easily extracted from pegmatites from spodumene, is that we've moved away from continental brines towards hard rock source lithium, because it's a more streamlined process to produce LiOH from brine, from spodumene. As I said, you have to go via a conversion process. So what that means from a hard rock geologist like myself is that over the last 5 or 6 years, pegmatites have started to slowly dominate the supply of lithium globally. So in green, we've moved from under 50% to now probably about 55-60% of lithium supply comes from pegmatites. So this is the rise of the pegmatites, a shift to hard rock source lithium. Also, it diversified supply. We can get supply from Australia, potentially we can get supply from Canada. We can start to unpick existing supply chains that maybe go via unfavorable jurisdictions or whatever. And as I mentioned, a lot of these pegmatites that were exploited were brownfields deposits, so we knew where they were, we knew they had lithium in. We could go to Tanko, which was a cesium mine. We could go to Greenbushes in Western Australia, which was a tin mine. We can go to Weiss in Namibia, which was a tin mine. We go back there and look for the lithium. But we're actually moving into a phase of greenfields lithium exploration now, which brings new challenges. And in fact, people think that, of the new projects coming on board, many of them appear to be pegmatite projects. So that seems to be where things are going, which is why, as academic geologists, we're getting interested in pegmatites when 10 years ago we'd never even heard the word, to be honest. So now it's what we do. So, what is a pegmatite? Well, the first thing you need to know is that clearly you need to have someone standing in front of it if you want to take a photo of it. So there's small granitic intrusions. On the top right, this is the Weiss area of Namibia. So this white thing here is the pegmatite. You can see it intruding into the country rock. This is Bikita in Zimbabwe, this cursive Pornex, which again was a historic tin mine, and it's now a very famous lithium mine. I have a lump of it here. This is my PhD student Lot in the blue t-shirt looking at the Plumbago North pegmatite in Maine. You can see the size of the crystals here. And in fact, this is one crystal of spodumene, which is the main lithium ore. This is quite a famous picture. So people think about pegmatites as being small granite intrusions with very large crystals. But the trouble is that some pegmatites can also have small crystals, and some have different types of mineralogy. So they're actually quite difficult to define. But very succinctly, to me, they're enigmatic, poorly studied minor granitic intrusions. If you want to ask a pegmatite expert, they're essentially an igneous rock, distinguished by coarse or variable grain size, but they have this very characteristic, what they call skeletal or graphitic directional growth habit. So the mineralogy, the minerals in the pegmatites, as you will see in a minute, are very strongly grown, they're very strongly orientated, because that's how the pegmatite is crystallized when it's been put in. So they're really strange things. Let me go, hold on. So we talk about LCT type pegmatites. So about 30 years ago, people decided there were 2 different types of pegmatites. Historic pegmatite research was either by gemologists, because that's where you can find a lot of gems, or it was very much a sort of minority pursuit by a few lone sort of standard bearers who were looking at these things. And they decided to classify pegmatites in terms of what they called LCT, which stands for lithium, cesium, tantalum, or NYF, which is niobium, yttrium, fluorine type pegmatites. LCT ones are the lithium-bearing ones, and they're S-type granites, so they're from crustal melts. So we think we form these granites, these pegmatites, by melting things like mudstones, shales, pelitic-type material. Simple mineralogy, they've got quartz in, they've got alkali feldspar, they've got white mica. They're very evolved, they're very silicious, they're very volatile rich. There's lots of fluorine in there, there's lots of chlorine in there, there's lots of water in there. They're rich in what we call incompatible metals. Things like lithium and tin are incompatible, so they concentrate in these melts. The primary ore of lithium is spodumene, which is a lithium aluminosilicate. There's a picture on the top right. Where are we? These are spodumene laths here. This is spodumene again, so it's this sort of, these are white rocks with white minerals in, with white ore minerals in. They're quite difficult to identify, okay? And I really struggle, and thank God for PhD students who stare down microscopes forever. So they're really hard to look at, they're a real challenge. So spodumene is the primary lithium ore. Petalite is also a lithium aluminium silicate, which is another lithium ore. There's things like lepidolite and zimwaldite, great names, which are lithium-rich micas. So the lithium deposits in Cornwall are zimwaldite bearing and lepidolite bearing. But the interesting thing about pegmatites is they crystallize from the margins inwards. So you get this zonation. So there's a picture at the bottom. Again, these things are like 150 meters long or 100 meters long. They're not very big. And you can see they have like a wall zone. Then they have an intermediate zone, and then they have maybe a spodumene zone, and then they have a quartz core. And what I did is I've got a bit of Zimbabwe real estate here. You can have a look at afterwards. This came from Dundee, okay? It's quite heavy. This is a picture. If you recognise train seats, this is ScotRail. You can see the thing, so that was on the way down. I took a picture of this. And what you can see here really is how zoned it is. So on the left, this is the margin with the country rock. We've got this thing here we call the albite margin zone, which is largely alkali feldspar and quartz with some micas. These dots here are probably tantalite oxides, maybe. Then you very quickly come into a mica zone, so very sort of silvery micas. We think maybe there's a margin of pollucite, which is the cesium ore, and then this is all spodumene. So they're just odd rocks. So the spodumene is what you want. You don't want the quartz, you don't want the albitic zone. So they are just really curious. So spodumene is the main ore. The problem is not all spodumene is the same. I mentioned petalites as well. So these are all lithium aluminosilicates. So when you get your granitic lithium melt, you melt something, it rises, it intrudes, and it starts to crystallize. And depending on the conditions where it crystallizes, you will either get spodumene or petalite. And on the right is this classic diagram where we have temperature. Sorry, I keep pointing up there with this thing. There we go. Temperature here and pressure here. And you can see these are the boundaries of spodumene. That's got lots of dollar signs next to it because that's what we want. Petalite, $1 sign. It's okay, but it's not great. And eucryptite. So what you find is if you have a relatively shallow pegmatite, as it cools, it will transform the petalite into spodumene. And you get this thing called squee, which is a spodumene quartz intergrowth. So petalite's got more silica in it than spodumene. And this image here is like squee. So it's spodumene and quartz intergrowth, which is a nightmare if you want to process it, because quartz is really tough, and it really affects the concentrate grades. So, people have projects and they say our spodumene is 6% lithium, but it actually could be squee, which could only be 4% lithium. So it's a real problem. Ore body knowledge is vital. Bring in the geologist, please. That's really important. So, what do? We have a lithium pegmatite that may be 1 to 2% lithium oxide. We produce a spodumene concentrate that may be up to 6% lithium oxide, but possibly less. That's the stuff we have to transport. It's not like copper concentrate, which is mostly copper. So 95% of the stuff you truck out from your pegmatite in the middle of Western Australia and drive it for 2,000 kilometers is not lithium. You take it to a refinery, and then you take it to a battery. So that's kind of the process of the spodumene. So, from a geological point of view, that's great. As I said, I'm not a mineralogist, but I've been forced to try and understand the mineralogy of these things. But what I find interesting is, of course, not all pegmatites are mineralized. You go to an orogenic zone and you find pegmatites in many places, but only a few of them will have lithium. And why is that? What is the fundamental control? If you can understand that, then you can kind of inform exploration a bit better. So, for me, the problem is that to make spodumene in your melt, you need to have a lithium concentration of at least 5,000 parts per million. And that's between 250 and 500 times continental crust. So you need to have a process that takes average continental crust and then, 500 times that, so you get lithium out of it. And that's a real challenge. That's the problem of making spodumene. So, what are the geological processes that we know that we involve to make a pegmatite? Well, two things really. We have to melt a crustal source. I said there were S-type granites, so we have some sort of shale-type material, pelitic type material. We partially melt that, we create a melt, a granitic melt. That melt then rises. Maybe it rises through shear zones, maybe it rises through structural levels. Again, we don't know how far these things go. And then it cools and then it undergoes crystallization. So from the margins inwards, and that's another way of increasing the lithium melt composition. This is why you don't necessarily find spodumene at the edge, because at some point you get to the point where we can actually start to crystallize spodumene. So both these processes concentrate lithium in the melt. And the question we're trying to answer is that, are they sufficient to take ordinary crustal material and elevate lithium to that level? Or do we need to invoke some sort of pre-enrichment in the material where we are originally melting? So do we need an extraordinarily enriched source of lithium that we then melt to produce a pegmatite? And those have very different implications for exploration, because either you're interested in the process or you're interested in the very specific geological environment of what you're melting. And so that would really direct your kind of exploration. So this is sort of the current area of research that we're looking at. There are kind of two different models, which I won't go into. They talk about pegmatites here coming off, granite bodies. So they're the last gasp of a granite body. Or they talk about pegmatites being small degree melts, first sweats, if you like. But ultimately, you still have to melt something and you still have to crystallize something. So, what do we look at? We look at, first of all, the melting process. How do we melt the continental crust? So I said we have a sort of shale-type material. If we don't get metals in the melt, we won't get a deposit. We'll just get a nice pegmatite with quartz and albite, but there won't be any spodumene in there because there's no lithium, basically. So the continental crust melts at about 650, 700 degrees C. It's a thermal process. We need to heat it up. We usually do that by burial. So you have some packaging material that you then bury, and then it starts to slowly melt, maybe 1 or 2% melt. And the composition of that melt is a function of several things. Obviously, the composition of the source, what minerals are breaking down to produce the melt. It's only particular minerals that break down. It doesn't all just disappear. So typically it'll be micas, so things like muscovites and biotites, which are hydrous minerals, will break down once you start melting things. So whatever's in that mica is now freely available, potentially to go into the melt. And then the other thing that really controls it for things like lithium, these trace elements, is the exchange of those elements between the melt and whatever minerals are present. So a classic melting reaction here is muscovite plus quartz plus plagioclase goes to potassium feldspar plus sillimanite plus melt. This is the classic muscovite dehydration reaction that you teach in Metamorphic 101. So, if your sillimanite really likes lithium, it will probably go in the sillimanite and not the melt. But if your sillimanite doesn't like the lithium, you'll get a lithium-rich melt. So, What minerals are present depends upon the source composition, but also the pressures and temperatures of melting and other things like the water activity and the redox state and things like that. So it starts getting very complicated. This is sort of, you know, metamorphic petrological problem. Igneous petrologists worry about things cooling. Metamorphic petrologists worry about things heating up. So what we know is that the micas like muscovite and biotite are the main hosts for lithium, but also cordierite, which is a low pressure mineral. And these are all common minerals in metamorphic rocks that come from mudstones, because they're all aluminous. So if you break down micas, you could release lithium into the melt, but if you have cordierite present, actually that cordierite will take the lithium in. So you'll produce a melt, but you won't have a lithium-rich melt, and you won't have a lithium pegmatite. Does that make sense, hopefully? So, okay. So then what we do, oh no, I think I've lost a slide. I've lost a slide. Anyway, I'll have to freestyle. So what I was going to show you is how we actually start to model these things. And we do it through equilibrium thermodynamics, and there are various modeling packages that allow us to predict at different pressures and temperatures what minerals are present with the melt at different degrees of melt. And then we can try and overlay things like how the lithium partitions between that. What I was going to show you is how that works for tin and tungsten. Can't do that. I'll show you how it works for lithium. So we modeled, for example, the melting of an average shale, which we assume was 100 ppm lithium to begin with. Again, we want to get to 5,000 ppm. So this is all theoretical work. We look at phase stabilities, which depends upon essentially thermodynamic equilibrium. And then we model the melting of the shale at different pressures. So if it's low pressure, you'll have cordierite. If it's high pressure, you won't have cordierite. But we found on the top right, this is my PhD student did it all. I can't claim it. The one in the blue shirt. So this shows you lithium concentration, the first melt step. We started about 120 ppm actually. And we found that regardless of, you know, the scenario, you can get maximum about 4 times lithium concentration at the minimum melt possible that you think would be extractable. You know, if you do 1% melt, you can get really lithium-rich melts, but that would never leave the rock. You need to get to 7 or 8% for it to basically be able to leave the rock and disappear. It's a sort of thermophysical limitation. So if you believe this modelling, there's no way you could get to 5,000 ppm from an average shale in one melt cycle. And what we also found is that biotite is a really, so this is muscovite breaking down, but you leave biotite, which is another mica, in the source, so that actually holds onto the lithium, so you don't get the lithium-rich melt. So cooler shallow melting, where you're just breaking down muscovite, will give you a lithium-poor melt, but potentially if you then break down that biotite, you will release it into the melt. So maybe deeper, hotter melting could do something different. But you know, if in the first stage of melting you can never get from an ordinary shale composition to the levels you want, then either you invoke the idea that you need some multi-stage melting, because then if you remelt the product, again, it's like distillation, you can bring it up again. So again, here, this is like the second melt cycle where we go from, you know, 400 ppm up to about 1,000, and at some point we can get to our magic 5,000 ppm, or we can form spodumene. And that's quite an interesting idea, because we find that where we have dated pegmatites, they're often the youngest magmatic event in an orogenic belt. And a mountain building belt can, you know, it can last for 60 or 70 million years as it evolves. And very often the pegmatites are the youngest thing. So actually invoking some mechanism where they are the result of a previous melting event, and all this has done is sort of jacked up the lithium contents, isn't a bad idea. The other thing is, yeah, maybe you just start with a lithium-rich source. And then instead of 100 ppm, we're already at 1,000 ppm, one of these lithium-rich clays, for example. And then that can get us to our point. So like exploring these ideas about how through a melt cycle we can, you know, jack up the lithium content eventually to the point where we could form spodumene is one of the things we've really been doing. So the other things we've been doing is we've been using, we go to the field, we look at real samples as well, and we've been trying to understand how, you know, we can use mineral chemistry to tell us what happened. This is the end result of all those processes, this is all we've got left, and this is our archive, so we have to interrogate this. And we like looking at mineral chemistry because it's arguably less susceptible to later alteration than whole rock chemistry. So we've been looking at things like tin contents, lithium contents of various accessory minerals to see if that can tell us something about the magmatic evolution, especially that crystallization history, and how mobile those metals will be. Again, I'm not going to go into the weeds of this because everyone will start to nod off. But, you know, trying to trace the metals through the system, see if we can see, you know, the appearance of a hydrothermal fluid which comes along and may lose the lithium, or how the lithium changes during fractionation is a really interesting sort of approach. And the third thing we've been doing, if I still have my slide, is we've been trying to date these things. So, as I mentioned, you know, trying to get some sort of greater four-dynamic, geodynamic evolution of how these pegmatites fit into a larger evolving mountain belt is important. And one of the key things to do is to be able to date those. Pegmatites are notoriously difficult to date. If you want to date a granite, you do uranium, lead, and zircon. They rarely have zircons, and if they do, they're undateable. So there are novel chronometers. So I have a student who's looking at cassiterite, which is the tin ore, which is often found in pegmatites, and you can actually date that reliably through uranium lead. There's other sort of, you know, as geochemists, we love all this stuff. It's you know, fancy new isotope systems, but there's ways of dating pegmatites. And if we can reliably date pegmatites, for example, the problem in Zimbabwe, you know, we think Bakita is possibly 2.6 billion years old, but it's hosted by greenstones that are 2.7 billion years old. But if we don't know how reliably, you know, how reliable the 2.6 billion year old age is, we don't really know how to link that into the evolution of the greenstone belt. So there's a lot of open questions about how pegmatites fit into geological evolution. Being able to date them is really important. So yeah, if we can date them and if we can look at how they fit in through sort of the broad crustal systems that these things pop up in, we talked about the fact that maybe deeper melting produces a lithium-rich melt, shallow melting doesn't. That's quite important, I think. So we're almost there, yeah. So really, you know, what are we trying to do? So our research group tries to understand how, you know, how do we develop metal-rich melts that ultimately come and produce lithium pegmatites. And we're trying to do that from a fundamental melting perspective to try and produce lithium-rich melts. But, you know, the great thing from an academic point of view, not necessarily from an exploration point of view, is that there's plenty of open questions. You know, we think it's really important to understand what you're melting, how that's melting, can we follow the metals through the system, can we use these modeling tools? And ultimately, we want to find where the elephant country is. So I'll leave it there. Thanks very much for your time. Happy to take any questions, and you're welcome to come and fondle my piece of Zimbabwe. Oh, that's a very good question. That's from a prospecting point of view. Well, I mean, the great thing about...
Can you repeat the question, please?
Sorry, yeah. It was how do you go about sort of what's your strategy for a prospecting strategy to try and identify these things and find them? Yeah, excellent question. So luckily in somewhere like Namibia, the exposure is excellent. You know, you can look at aerial photos, and because these bodies tend to be really white, they just stick out. And so then you can just trundle along in your 4x4 and have a look at them. So that's kind of the first order thing. The Weiss area in Namibia was explored for tin. You know, for 40 years, the big tin mine there was run by Eskom, the South African power company, for about 30 years, and it was shut down in the 80s. So there's a lot of historic data from exploring for tin that then we can go back and say, well, you know, are these lithium bearing? What's interesting about that area is there are multiple generations of pegmatites, some of which are tin bearing, some of which are lithium bearing, some of which have both, some of which have nothing. So the exploration geologists there have, you know, systematically comes down to geological mapping. You know, they've gone out there, they've tried to understand the mineralogy in the field, take samples and things like that, and see if there's a pattern and stuff like that. It gets a lot more challenging in places like Brazil with the cover, Southeast Asia, you know, so Southern Africa is a great place to do this because, you know, there's just fantastic exposure and so many any of these things. Yeah. But they don't stand out in things like geophysical surveys. You know, they're not big enough as a gravity anomaly or anything, so the kind of remote sensing perspective is challenging. Yeah. Extremely challenging.
Thank you.
Hi, Nick. Norman Jackson from Seton Sluice.
Hi.
I'm very interested in your talk tonight. It's been excellent. The processing of the materials, the melt, as you've described it. Many of the deposits will be in remote areas.
Yep.
How do you, or do any of your calculations take in the cost of actually the preparation of it to get it into a
Yep.
usable source? Because many of these places have no power. You know that unless you're going to build a power station, how are you going to prepare this in a green manner?
Yeah, yeah. No, that's an excellent question. So you're right, many of these, so to repeat the question was on a microphone. Yeah, so many of these places are in remote localities. You know, you've got several challenges because the bodies are so small. Often you've got 5 years of mining life, so why would you invest in a huge processing plant in your mine? You know, that's the first problem. Even if you can concentrate it, if it's 5 or 6% lithium, you know, you've got huge costs in the transportation of the ore because you're trundling it thousands of kilometers or so. And absolutely, it's diesel generators. You know, so if you talk about green metals, but a lot of the extractable mechanisms is not through this. Yep. Okay.
John Beatty, Bedlington. Given the complexity of extracting the lithium from sticking a pin in a haystack, isn't it, in lots of cases, how much research is going on to replace the function of lithium in electric batteries? And there's a second, just a comment, the second one, which goes back to the map at the very beginning. And you said this is the non-political problems of searching for lithium. But given the amount of hard rock bearing stuff in Canada, it might explain why Mr. Trump's advisors have suggested that bringing Canada into the United States might be quite useful.
Annexation of... absolutely. So, sorry, what was the first part of the question again? I was thinking about the Trump...
About replacing lithium.
Yes, that's right, replacing lithium. Sorry, it's been a long day. No, that's a really, really good point. So there's a battery group in St Andrews who are researching sodium-ion batteries because they feel that, you know, sodium is plentiful. You just evaporate the sea. They feel that the supply restrictions of lithium are going to be so extreme and so pervasive that actually we will move to different technologies. And, you know, these predictions of how much lithium we need in 2035 is for the birds, because by that time we'll be using different battery technologies. So I think a lot of people, you're absolutely right, you know, are looking at different battery technologies. Using sodium seems to be the one. You know, not everything needs a lithium-ion battery. Solid state storage doesn't have to be lithium-ion. Truck batteries don't necessarily have to be lithium-ion, I don't think, if we ever get to that. So this is something we've been thinking about as well, you know, where will actually things go in 5 or 10 years, and what would be the other technologies that come on? So I think, you know, copper is unsubstitutable. We're not going to substitute for copper because it's so relatively abundant. It does an excellent job of what it does. Why would we look for something else? Lithium is really supply constrained, has issues with supply chains going by China, and I think people are looking for, you know, and it's not so embedded as a technology that you couldn't just switch and do something else now. So yeah, I think that's a really important point. On the Canada one, no comment.
Anyone else in the room? Any questions? No, it appears. Here we are, Dave Granger.
Nick, will you be able to give us that slide that's missing?
Yeah.
I'll
find
splice it in at some point in the future.
Yes, I can. Yeah, it was probably the most complicated slide of the talk, so maybe I purposely removed it.
Yeah, so if you go to the YouTube NEIME channel, the NEIMME, this will recording will be kind of there with the added slide at some point in the future.
This is actually was the slide to your point about concentrate. So on the bottom right, this shows you the cost, operating cost of several pegmatite deposits, and the transportation is in red. So you can see for the one in the DRC, 2/3 of the cost of mine operation is shipping the concentrate out, basically.
Well, thanks, Nick. That was a very interesting talk. David Granger from Sunderland. Yeah, you're talking about the salars in South America. A few years ago, my wife and I went on a holiday to Bolivia, of all places, because a relative of mine was working on, he was a mining engineer, on a new silver mine in the south of Bolivia. And we went actually to the Salar de Uyuni,
Right, okay.
which is an absolutely fantastic place. And we drove, or we'd taken, right across the Salar to this little island in the middle, which had a fantastic euphorbias. But it is absolutely huge, and it's an absolutely incredible place. But they don't, well, at the time they weren't extracting lithium there, but I'm not sure if they are now. They're extracting salt on a relatively minor scale around the edges. But, I mean, I'm digressing. One of the fantastic things was finding a cyclist in the middle of this salar. And he was cycling, a Belgian guy, cycling from Cape Horn to North America.
Wow.
And it's the most bizarre thing to see this dot on the horizon in the shimmer. Okay, that's beside the point. But what do you think about the viability of these sorts of lithium in this country, like Cornwall, which is the hard rock, and the Pennines, which is the brines, in effect?
Yeah. I guess in short, I don't know. I don't know. I think, you know, it comes down to I suppose, I don't understand how you define a resource. I'm sure you can define a resource for that. But I think it comes down to the reliability of the extractive technology and the costs therein. You know, I think so that there's people worldwide looking at direct lithium extraction. It's not something I'm an expert in, but you know, people do seem to feel like there's a way forward. There's a project in South America as well where they have at least a pilot plant going. You know, at the moment the market sentiment seems to be going towards pegmatites, and I think one of the advantages of pegmatites is that it's a classic mining operation. You go and dig a pit in the ground, you process it, you sell it to your favourite smelter, and you know, both the salars and brine is you know, a totally different way of extracting metals from the ground. But it's interesting because I think we need to find new disruptive ways of getting metals. You know, there's been noises about metals from brines and volcanoes and things like that, and I think, you know, if it is or isn't ever going to be, you know, maybe it will become a great way of getting lithium or not, but actually thinking about novel ways of getting metals that we need without what is actually a very kind of primitive way of digging up massive amounts of ore and crushing it in a jaw crusher and creating huge tailings piles. And, you know, it could well be that it turns out to be a very clean and ultimately very low-cost way of extracting metals and lithium and things like that. So I think it's really interesting. You know, I don't know enough about the economics of it, but yeah.
It's not a question, it's a comment really. I guess there's a question behind it. Given the expertise that you've just referred to, as I talked about, the expertise in this area amongst coal miners, coal mining engineers, go back to lead mining in the North Pennines, and the innovations that 200, 300 years ago, working men in this area were discovering to extract those minerals from the ground. And it just strikes me that it seems really sad that expertise has almost disappeared. As the industries have been killed, the expertise has been killed, and suddenly it's exactly that kind of expertise that's needed, and to go into fields that the kind of field that you're into. Just a sad note to end on.
No, I think that's great. I mean, you know, we find, to turn it into a more optimistic note, that students are interested in the resources industry in a way. You know, 10 years ago, most geology students went into oil. That's where the jobs were, for example. And mining didn't really appear much on the radar, I suppose. You know, there was obviously Camborne and Imperial that were quite big mining schools at the time. But now there's actually a lot of appetite to learn about resources, metal resources. People tend to then go to Australia for the jobs because the jobs aren't necessarily here. But, you know, I think the tide is turning to a bit. It's a real challenge still to get people into universities to study geoscience, and that needs to be changed. I could talk at length about that, my opinions. But, you know, I feel like the government's becoming aware, the public's becoming more aware about the need for these things. And, you know, I feel relatively optimistic that over time we will start to sort of build up those skills a bit more. You know, and the mining engineering course restarted at Camborne this year, where they had shut it down a couple of years ago. So, yeah, I'm positive. Great.
Any more questions from the floor?
Yeah.
No, to tell you the truth, I think they're all frozen. There's so much to take in there that they'll think about it in an hour's time, saying, "Oh, I wish the hell I'd said something there." But that's the way it happens with lectures, isn't it?
Yep.
Wonderful. Well, thank you very much indeed. And I'm sure everyone has enjoyed the detail you've given us this evening.
Thank you.
And on that note, could I call upon Norman Jackson, please, to give a vote of thanks?
Nick, what a wonderful talk. You began by outlining the main areas of where these precious metals lie. You moved on to the chemistry, and as a mining engineer, much of that I didn't quite understand, but I knew that it was accurate by the people round about me who were nodding in acid. But it is very, very nice to have somebody like yourself to come to this institute, where we usually get some very high quality talks. Yours tonight has been in that category. It has been excellent. But on the side, the one thing that worries me, I like to see a plan of where we're going. Mm-hmm. And the sad part of everything that I see in the world today is there isn't one anywhere. And to think of the dates that we're trying to meet, like 2035, which is 10 years away, and knowing how long it takes to sink a mine, start a mine, get the planning permission, with all that's going on, gives me a great sense of wariness. But perhaps at my age, maybe I shouldn't be thinking about it. But at any rate, on behalf of all of us here, thank you very, very much for your excellent talk. And could everybody join me, ladies and gentlemen, in showing our appreciation in the normal manner?
Okay, there are a few closing points. The first one is, if anyone wants to come down and have a look at the rock sample here, you know, you're very, very welcome. Take care on the stair as you do it. I think that just about leads us into the next meeting, which I think Andrew explained to you quite carefully. Another point I'd like to make is we are very, very closely allied to the IOM3. So please, if anyone knows anyone or yourselves are in IOM3, you're more than welcome to come along to all our meetings, and could you tell everyone else what we do here and how wonderful the lectures are, proven by tonight. So wonderful. Have a safe journey home. Can you please make sure that you've signed the log and the books so we can be sure who's been here, and we do get a small remuneration for everyone who attends. So make sure you come along on Monday, for those of you who can anyway, because as I say, Les Turnbull's giving his talk, and Les is an absolute authority on railways in the north of England. I'm sure if you don't know that, you'll certainly find out on Monday. So you're more than welcome to come along to that and give him a good cheer. Other than that, have a safe journey home, and as I say, sign the book as you go out if you haven't already. And I look forward to seeing you. I'm sorry I won't be here on the 27th, but I will be here next month for the lecture, and hopefully they'll let me stand at the front again and help the speaker along a little. So thank you very much, all of you, for coming along tonight, and I'll see you then. Thank you. Bye.
that's a big thing.
Yeah, this is the spodumene. So this is the wall rock. That's where it intruded, and it crystallizes like this.